Next up, we have Ken Rawlings. Ken is a senior system analyst in the High Performance File Systems group here in Indiana. He's currently serving as the OpenSFS liaison to the Lustre.org working group, and he's acting in continuing improvement of Lustre.org. Ladies and gentlemen, presenting Ken Rawlings.
Thanks, Steve. Steve was saying, my name is Ken Rawlings. I'm a member of the High Performance File Systems group here at IU. While I'm presenting this talk, this has very much been a group effort, this project. The project is called Zester, and I'll talk more about it here in a moment. So, what caused us to go down the road of this project was we have a site-wide file system here at IU called Data Capacitor 2. It runs Lustre 216. LDISC-FS, MDTs, and OSTs, 5 petabytes. I think probably the most important thing on this slide that drove us to go forward on is that we have 1.5 billion inodes. And in addition, so we didn't just get to 1.5 billion inodes today. It's taken a while, and so we've been reporting against this file system for quite a while, and we have an existing workflow, basically, where we generate a metadata DB to report against. And we do the standard sort of things that you might expect, but we want to have it all the way down to a file level. The way that we do this currently is that we use Lustre, which I'll talk about here in a moment if you're not familiar with it, to essentially do a dump of the MDTs to get metadata information. Then, for each of those files, we then go through Lustre to do a stat. That's worked pretty well for us, actually. But as the file systems get larger, and specifically since we broke 1 billion files, we started. Oh, sorry. Thank you. Since breaking a billion inodes, we started running into issues with just the amount of time it takes to do that sort of stat. So we have a file system, an upcoming file system at IU that's going to be Lustre 2.8. Well, we specified an RFP for it for Lustre 2.8 and with a ZFS, MDT, and OST. And it's going to be larger than our current system. So the situation that we found ourselves in is that we need to have this sort of capability going forward with our new file system. So one of the core pieces of the way we do things now is that we use Lustre. And if you're not familiar with Lustre was written by David Dello at ORNL. Basically, what you do is you point this at an MDT, and it generates a really nice parsable text file with all of the MDT information, or all of the Lustre metadata information on the MDT. Just separated by essentially almost like a CSV sort of format, go through line by line. What we ran into is that for our upcoming ZFS system, there's no equivalence of Lustre for ZFS. So what we decided that we needed was that we need an equivalent solution to our current system for ZFS. And it's sort of a stretch goal, basically. So as I was saying earlier, the big struggle that we've had since our file system has gotten a lot larger is the stat time that it takes. So what we wanted to do is that if possible, in addition to getting just I suppose I should have mentioned before, I apologize, so when you're getting information from the MDT, you don't have file size information. So that's why we would go through and do the stats. So if possible, we wanted to be able to build a system that didn't require us to go through and do manual stats through Lustre. We've stayed very focused in this project. As I was saying before, we have an existing metadata DB format that we're used to providing to do the sort of reporting that we need. And for that, we need path, UID, GID, mode, timestamps, and size. So we set out to see what we could do. in two stages. First, as I was saying, essentially duplicating on a certain level what Lustre does for ZFS, and then going through that sort of information on the OST as well, and seeing if we could get together and basically compute file sizes without actually going through Lustre itself. So, additionally, we had some priorities that we set on this. I think one is that for the reporting needs we have, it doesn't need to be perfect. This isn't in support of something like HSM. But if there were going to be error bounds, if it wasn't going to be perfect, we wanted to have an idea of, if there were going to be issues, we wanted to know how close it was going to be. We didn't want it to just be sort of out there in the weeds. As I was saying before, it was important for us to be faster than Lustre stat. And one of the things that I'll talk about over the course of this talk is we've tried to be mindful of scalability. And the metric we sort of use is that we want to have the speed that this runs at to be measured in days, not weeks. We wanted, if at all possible, to not be parasitic on the file system. And we wanted there not to be any custom code run. Well, okay, so we were okay with running code on the OSS and MDS, but we didn't want to run any custom code on the OSS and MDS. And a big part of that is that when a file system is like we have, we're not running with backups, right? So if we're doing something, directly on our OSS and MDSs, we didn't want this exploratory. We basically wanted to be very careful. And when I say we, I should also mention, because I think I forgot at the beginning, that as I said, this has been a group effort. My team members, Sean Slavin and Tom Crow, in the audience right now. We sat down and put this together in a variety of ways that I'll talk going forward. So to know, this of course isn't all about ZFS and Lustre, but on a certain level, I wanted to point out that from a Lustre standpoint, it's Lustre and if you run ZFS as a POSIX file system are at kind of the same hierarchical level, and down below them are they're built on these lower level pieces of ZFS. And the two most important ones that we had to work with were first the data management unit, which is basically, from this perspective, essentially an object store. And then above that is the ZFS attribute processor, commonly referred to as ZAP. And that's essentially a key value store that's used to store directories, to store directory lookups. So in order to get information out of these lower levels, it turns out there's a standard utility that comes with ZFS called ZDB. And if you use Lustre ZFS and you're already familiar with ZDB, check it out. It's a very, very powerful utility. It'll do quite a bit of provide quite a bit of information to you. It has you can keep passing it Ds for debug info. And if you pass ZDB, DDD data and a data set, it dumps all of the objects in that, or metadata, I should say, about that object from ZFS file system, or from the ZFS perspective. This object information, if you dump this on an MDT, or on anything, but particularly important in this case for an MDT, will give you path, timestamps, size, GID, et cetera. Also, importantly, from a Lustre perspective, it includes extended attributes. On the MDT, it includes trusted.love. On the OST, it includes trusted.fit, which are the two key extended attributes we needed to start to piece things together. We found that ZDB was somewhat challenging to parse. There's things like at the beginning of lines, you'd have a mixture of spaces and tabs, things like that. We were sort of worried about the beginning, and as I'll talk about later, if you look at the code, you'll see places in there that we're trying to be proactive about parsing issues, but so far we've had pretty good luck with this. So to go into a little bit more detail on what you see, This down at the bottom is an example of an MDT dump, or sorry, an object from an MDT. In this case, you get this a ZFS object ID, so it's ZFS object ID 199. It's a plain file. So path, there's your Lustre path, UID, GID, A time, et cetera. And just for space, I've cut out the rest. But as I was saying before, importantly, we do get the extended attributes. And importantly, in this case, the trusted.love. So with Lustre, at that point, for the trusted.love, that will contain information on where that file, those file stripes are on the OSTs. So my colleague Tom Crow had done some great work with extended attribute decoding. He had actually put together an extended attribute decoding script that provides when you have this this information, given the trusted love. Now, this wasn't from a ZFS perspective at the time. This was earlier. But when you had that the trusted.love, it was able to provide us the OST index and object IDs. But at this point, we didn't have the ability to go from the ZFS decode format to the ZDB format to what Tom scripted. As it turns out, Chris Marone, who's out there somewhere, had written this utility called ZFS object to FID. And so what this does is that it uses ZDB if you have a ZFS object to then turn that into a Lustre FID. And in order to do that, it had general ZDB EA decoding logic, right? So we then used that to move forward, and we're able to start decoding the trusted.loves from the ZDB dump and feed it into Tom's script. And oops, I think I how to says escape. Oops, sorry. Let's see, I'll probably play here. I guess play from current slide. Fingers crossed. Cool. Okay, so then moving on. Once we then had the OST index and the object IDs, we then would needed to go to the OSTs to then discover the file size information. So in that case, I was talking about FATZAP before. So with FATZAP is essentially, like I said, is a key value store or key value format that has the lookups. So this is what we used for directory lookups. So basically, you're coming in and with the Lustre object ID, we come in and and I've got a more specific example here later, but with object ID 265, you come in that ties. This is essentially, if you're familiar with the O directories and OSTs, this is where it gets tied together. So that's saying, object ID 265 maps to ZFS ID 421. Then we go down here to 421, and then that has the size on it. So now we have all of the pieces necessary to put together this triangular size, and the OST objects then have the trusted fit as well. So to make this a little more concrete, so let's say you're doing a dump of MDT 0. You come along, you've got a ZFS object, so you've got this is a Lustre file that's foo.txt with a trusted.love like I was showing before. You go through, you decode that into its OST IDX, to the OST objects, object ID pairs. You then go over to OST 0, as I was showing before. This was the example before. You see you've got on the FATZAP, you've got a from and to. Then on the ZFS object, so you go 265 to 421, 421 to 220, 182. Then you do the same thing on OST 1. You add them together, and you have the size of your file. So we started on this is experimental, and we basically were piecing things together by hand. Things seemed to be working, so we went ahead and turned this into an actual project. We called it Zester as homage to Lustre, and David Dilla was very kind in allowing us giving us to do that. We wrote this. This is probably one of the biggest surprises to me so far. Is we were able to. So we started writing this in Python, and really did think that we were going to end up having to likely move to a compiled language of some sort. But actually, it's been working pretty well for us so far. We're currently Python 2.7. Just because that's what we had the most experience with in the group. Probably going to be, we've looked into moving to Python 3, and we'll probably be making that move here in the not too distant future. We started with an in-memory representation of everything I was just showing you, and we were actually kind of surprised at how well that worked as well at the beginning, and so in the beginning for experimentation and moving forward. We were actually able to use that format to get up past 1 million files for testing. But then basically Python seems to have some pretty hard memory limits in it that we weren't able to get past, and we knew we were going to have to go to a persistence format anyway. So we moved to SQLite for that. And the original idea there as well was to have that be sort of a temporary thing, but actually SQLite has worked surprisingly well for us. But all the code that we've written for this is using is basically it's Python just a standard DP API, and we've used portable SQL. So we've been mindful about the ability to move this to another RDBMS going forward. So this is basically how the Zester tool works. We go through, we parse the MDT and OST ZDBs. We turn that representation into an intermediate SQL persistence layer, which the SQLite I was talking about. So you have ZDB representation essentially in SQLite. We then go through those persisted ZDB, MDT, and OST databases to compute file sizes and assemble things. And then in the end, we generate a metadata DB that represents the state as we think Lustre sees it. So, as saying, each MDT and OST ZDB data set we dump into a separate file. As I was saying, also we've run into some parsing challenges, but it's like I said before, it's been surprisingly robust. Just to show one of the things we've tried to do is put information in here going forward. When you all look at this, the code, basically this is the schema that we're using to represent the ZDB information. So the ZFS objects I was talking about and FATSAP. And so then what we do, and I think that this is documented in the repository I'll show later as well, but we key off of file names for the tool. So you basically pass in, an MDT dump as MDT underscore, and then the index of that MDT, and same with OSTs. So just to do a quick run through of how this then works in practice. So we go through the MDT dump and go and find all the ZFS objects with trust.love. We decode that trust.love into the OST object ID pairs. We translate each of those object IDs into the basically follow it all the way down to get the target OST object. We then query that object for its size and do that for each, and then sum those all together in getting the final object size. And at that point, we generate the metadata DB that I've been referring to, which what we try to do is get that something that's like, that's what we think that Lustre, that represents file from what Lustre believes it is, or that we think Lustre believes it is. And so then we then output a metadata, each metadata, so we output a row for each of these, for each of the files in the file system. And then similarly, as I was saying before, we try and key off of file names to make things, because you don't know how many MDTs and OSTs are going to be passed in, so we try and be dynamic there. So in this case, we come through and you have, let's say in this case, well, I guess I have a generic there, but ZDBs get turned into a DB file for, as I said, for each MDT and OST. Then those DB files get turned finally and coalesced into the metadata DB. So so as part of this, is we've gone through and done a fair amount of work, sort of sanity checking this, but the proof is in the pudding on an actual Lustre file system. So we spent a great deal of time going through and testing this in various ways. So we have a test system that we've been using with 10 OSTs that we use with. One of the things that particular, well, various mode sizes, depths, all that. We've also been very, very careful about testing at a variety of stripe sizes because one of the most subtle things about this, of course, is then piecing things together from an OST standpoint. So we go through and we create a group of files, then we go through and test all of those, or I'm sorry, we go through and Lustre stat all those files. Because in the end, we do want to know exactly what Lustre feels that file is, and so we want to match things up exactly. So then we have a script for each of these pieces. Then the final script basically goes through. So you run this against your MDT and OST ZDB dumps. You have a metadata DB that's the way that Zester thinks things are. Then you run this canonical stat generation utility. Now you have another database that you're sure is how Lustre views it to be. Then we have a tool that basically goes through one by one and compares those. So where are we now? Still a work in progress, but very promising results. As I was saying before, we went into this knowing that some level of error might be acceptable, but we've managed to break. I say millions of files here. We've broken 5 million files now and haven't seen any issues. The one thing there is one subtlety here, and that's that because of the way that ZDB dumps work. Well, here I can just, let me go back. Yes. So if you look at the 8 time here, we're actually just getting it up to the seconds, right? And so we need to go through and basically parse that as text. And that's the level of accuracy that ZDB provides us. So back here. So with that, we found that we're not able to get more than currently than a 2 second variance in precision on timestamps. But that's currently the only issue that we're seeing. We've been testing primarily. We did some early testing against Lustre 2.7, but since our RFP specified 2.8, we've been testing almost exclusively against Lustre 2.8. And I think one of the things that we've been sort of surprised about, as I said, particularly with Python, using Python, is that the Zester tool itself currently isn't the thing that's limiting our ability to scale up. It's our testing infrastructure. That we were running this, we don't have a large testing system for this, but we do think even with the infrastructure that we currently have, that we're going to be able to test this up into the tens of millions in a fairly reasonable period of time. We're hoping that about the time that our current testing infrastructure, we're starting to break down in terms of how long it's taking to go through this phase. So I was saying that Zester isn't what's currently limiting us. What's currently limiting us is that we have to actually go through and create all those files, and then we have to actually go through and stat all those files, because in the end, we need to be able to check to make sure everything's working correctly. And then the plan is that hopefully it'll dovetail well that about the time our new system comes online, we'll switch over to using that, and then we'll be doing it against our actual new file system. As I mentioned before, part of the whole purpose of this is to be able to go against a file system with billions of inodes. So while we're not there yet, and our system isn't there yet on a ZFS standard, we're trying to keep that in mind sort of at all times, right? So far so good. We don't see anything particularly scary going forward to getting to that point. Sort of one of the things that we're keying on, as I was talking about before, is the days, not weeks. Similarly, as long as we can stay where the number of objects that we're processing is measured in the thousands, that ties up well with that, and we are there. Currently, the tool you just pass it in all of your MDT and OST ZDB dumps, but it's sort of in one fell swoop. But that parsing, it's sort of inherently parallelizable. You could run that on as many machines as you want. There's no sort of interplay that's necessary between them at that stage. And that's definitely something that we'll be doing. We've done extensive profiling of the system, and currently for ZDB parsing, it's actually, it's funny, I showed you before the A time. Parsing that into a timestamp that we can use and store, we use the Unix, well, it's through Python, but we use the Unix system call, or the standard library call, strp time. And that's where the profiler shows us at. So, we might get into, custom date parsing territory to get a little bit more speed, but we figured that was going to be more of a source of bugs. Since we moved to SQLite, we're actually not using that much memory. Where SQLite's using quite a bit, but that's sort of handled behind the scenes. And if we do, as I said before, if we do need to move to another database server, we should be in a good shape to do that. MySQL or a PostgreSQL, of course, is going to have all sorts of optimizations that we can use for this. Finally, as I was referred to a couple of times, we've had surprisingly good luck with Python for this. Our hope is at this point that, while we'll probably need some sort of C extension sooner or later, so far we haven't, and Python is pretty easily extendable in that way. One of the other things that I wanted to mention is that, so I talked before that this is done in stages. You go from a ZDB dump to a SQLite file that represents that ZDB dump, and then finally to a metadata DB. We found that having that available, I mean, that was just sort of as part of our process, but we then had those available to go through and look at ourselves while putting this together, and that's proven surprisingly valuable. We've been using it to investigate alternative ways to verify, to make, even before we get to the formal testing stage, to verify sort of ahead of time that things are working well. And just sort of in general, there's this idea of having a queryable database of the ZFS layer underlying a Lustre. It's very enlightening to be able to look at ZFS Lustre under the floorboards. We're already starting to look at ways that we can use this for file system forensics. But as I talked about before, even in its current state, it's very helpful in this way. We don't store all of the information that's available in a ZDB dump. We're storing what's targeted for and focused for this project. But as I said, this has been valuable enough that more will definitely be added over time. So, where are we going to be going forward? Well, first off is scaling up and testing. As I said, we're at 5 million on our way to 10, and we hope to get into the tens of millions with our current system. But then, of course, we need to get this up into the billion class. We've been focused on Lustre 2.8. We want to look at try with other Lustre versions. We haven't tested against DNA2 yet, and that's something we want to do. We're focused for our current needs, as I said, for these the metadata that we currently report against. that we currently use to report against, that's pretty much exclusively we care about regular files. So that's what we've been focused on. So Zester currently doesn't formally handle directories. We know how to do that. It's going to be doing that in the very near future. As we have been doing, as I said, pretty extensive testing from an integrity standpoint. We want to formalize our unit integration testing approaches, dive into the source code of ZDB and Lustre itself, and then finally, the Lustre itself is a moving target, which is a good thing. So things like the layout enhancement work will definitely impact this, but we're aware of it, and we'll be keeping track with it. So with that, thank you all very much. Please feel free to contact us at hpfsadmin@iu.edu. I want to thank everybody in the Lustre community for the culture of sharing. I mean, the amount of information that's out there in the code I referred to Chris's ZFS object did. It's what makes these sort of projects possible. And also, as I said, this has truly been a group project with all of my colleagues at HPFS at IU. And the source code for the tool that I've been talking about is available now on GitHub. That should be live. So on GPL2 license, and we'd really love to work with the community on this. So with that, if there's any questions, I'd be happy to answer them.
You mentioned that Zester currently looks things up primarily by file name. Is it also capable of looking up the information, for example, file size greater than foo or file size less than bar?
So yes. So the way this part is a little bit in flux, which is basically that final metadata DB format. What we've used in the beginning for that, it actually really does match what we use for our current system at IU. So I just want to tell you, when you actually go look at it, this is talked about up on the GitHub repo in the README. But there's some columns there that we don't actually do yet. A little more in sync. But to answer your question specifically, since this all ends up in a SQLite database, you can do the query on that. So you basically have so once it gets to the SQLite database, it essentially keys off the path, right? But then you have all the other columns. By default, it's not doing indexes on anything other than the primary key, but you can certainly do those types of lookups. And that's one of the things that we thought about is that going through and adding additional indexes or transforming that database into further things as well. But yes, even in its current form, you should be able to do that.
Thank you.
Hi, Ken. Have you looked into using Robinhood as a database for the metadata? And if you did look into it, why did you end up going down this route?
Oh, absolutely, sure. So yes, we're very familiar with Robinhood, and we like Robinhood quite a bit. In fact, we won Robinhood on one of our smaller file systems, and actually I've done a fair amount of querying against the Robinhood databases. There's a couple of things. First off, I mean we've had struggles with Robinhood at these scales, at the current scale, and that this new system is going to be larger. We also for running Robinhood, you're going to be statting the file system. So I guess there's two pieces to this. One is the information gathering, and so that's the avoiding the stat aspect and the scalability is what kept us from using Robinhood itself to do this. But you also asked about the database. The way Robinhood stores its metadata information is different than what our colleagues that do the reporting are used to. And so we went ahead and for this used our current metadata. But basically, the primary difference, as I recall, between what we're doing and how Robinhood stores data is we actually store the entire path, just because for ease of querying, whereas Robinhood actually breaks things up into pieces. the path into pieces, which are then sort of joined together, which has its advantages and disadvantages depending on how you're querying what have you. But I suspect, I mean, it's interesting that comes up because in a conversation recently, one of the things that's nice about doing things, I mean, I don't know if we'll end up being able to stay with SQLite, but that's nice about SQLite is you can do these sort of transformations. And you can imagine a situation where you took the metadata DB that's generated and then transform that into a more Robin Hood-like representation, which then would allow you to do things much easier, like finding out all of the parent or children of a certain directory, because as it is now, that's all just it's just a path. And it would also be more space represent, easy to represent. It would be smaller in space as well. But advantages, disadvantages either way. And we feel that we can do transformations when needed on that sort of thing. Please.
I guess. First question, have you looked at integrating directly with libzfs instead of doing ASCII dumping and parsing and things like that?
Right, so I think what's interesting, so I was thinking more from a libzpool perspective, but I'm familiar with libzpool. Are we on the same page?
Well, maybe it's not libzfs. I mean, you could essentially do what ZDB does, right? I mean, there's two options. I think ZDB, you could dump it into a format that's easier to parse, right?
Yes. And as a matter of fact, so I mentioned this before, not going all the way to that direction, but that at the ZDB. So we've taken this from looking at it from a Python perspective. We haven't been diving into a lot of C source code. At the same time, my colleague Sean Slavin has gone through. So I mean, with the parsing of the times and what have you. I guess there's two big issues we run into. One is the parsing of the times. There's no, and I don't remember Sean was talking about that. Like you can see where ZDB turns it into a human readable form, and then we doing it right back, right? So yes, we've looked into the idea. We haven't gone too far down the road from a libzpool perspective, and we've investigated it, but more from looking at potentially and also potentially working with the ZFS team to improve ZDB in that way, and also just to make it more easily parsable, just in sort of like a JSON, whatever format, right? But this, I guess, goes all the way back to that we didn't want to be doing. So ZDB, when you're running this against your file system, you are going to be running it as root, right? And we wanted to avoid custom code ran as root as well possible. But as we have more confidence with this, yes, absolutely.
Okay. And second question. I guess tying into the earlier question, is it possible to run it in just a scan mode where it doesn't go into a database, so it just dumps out a list of files and you have some criteria or something? So
in its current form, I mean, just getting things ready for the talk and getting the GitHub repo available and what have you, currently no, but that's on the very short list of things to do. And basically, if you look at the bottom of the file, Python file, you can see where it's basically doing the persist and then, then the parse and then the assembly. So not currently, but yes, absolutely. And in a similar way to having it be in a mode where we can have it being able to run. I don't know that in the near future we'll have it automatically doing any parallelization, but you might not. You may very well want to be just doing one MDT dump to ZDB, right? So making it more modular like that is definitely on the near future game plan.
I was going to say.
Thank you all. Thank you, Steve.